paper 1 from November 20. Starting off with amount calculation for solid, 12 grams of ethanoic acid, for which we would need to use N equals M over big M. Mass, 12 grams over the molecular mass, big M, as given by the question 60. But what's the unit? Would be useful for you to know what the unit for molecular mass is. That would be grams per mole. So that when we do the division, we would end up with 0.5 mole. Now, once we have 0.5 moles, the question is, how many carbon atoms are there? What we know is that for every mole of any substance, there would be the Avogadro constant number of particles, whether that is the number of atoms or molecules. In our situation, we want to multiply the mole by 0.5 times 6.02 times 10 to 23 atoms, which would give us 3.01. Sorry, there was a calculation error. Let me go back and put 0.2. If we multiply the Avogadro constant with 0.2, we will end up with option C. Next question is about empirical formulae. What formula do we have? Chemical formula, molecular formula, empirical formula, structural formula. Empirical formula is what? It's the chemical formula with smallest whole number ratio. So what we're looking for is, like the option I, we can no longer divide the number of carbons, hydrogens, and oxygens, which means C2H6O is a formula with the smallest whole number ratio, unlike option II, which can be turned into CH2O. That will be the empirical formula. Like option I, C5H12 is no longer divisible to become smaller whole number ratio. 1 and 3 only is our answer. Stoichiometry question, where we're dealing with combustion of ethane to produce the product carbon dioxide and water. How much ethane, how much volume of ethane gas will have been used is the question. So what do we need to do? We need to set up the initial and final. Initial and the end volume of gases starting and finishing. We don't know what it is for ethane, so we'll put the volume of ethane used as X, but we do know what it is for oxygen. And at the initial, we also know the volume of carbon dioxide present will be 0. But at the end of the reaction, we know that volume of carbon dioxide present will be 40. And we can assume that water vapor volume will also be 60. Why? Because 4:6 ratio between the two products tell us about 40:60 relationship as well. Now, the question is, if 40 moles of carbon dioxide have been produced, 40 cm cube of carbon dioxide have been produced, we must think that 70 cm cube of oxygen has been converted, which means that 70 cm cube of oxygen will be remaining. That also means that 20 of ethane will have reacted, meaning 50 will be remaining. Answer B, 20 cm cube will have been used. Mass spectrometry will give us the relative abundances of multiple isotopes. In this case, we're given 3 isotopes with mass numbers of 24, 25, and 26, where 24 atomic mass is of the highest abundance. We are often asked to work out the relative atomic mass given relative abundances of different isotopes. For that, we would need the exact, precise abundance percentage. Unfortunately, we're not able to exactly figure out the percentage abundance of each isotope. Is the 24 mass isotope 78 or 79%? Is the 25 mass isotope percentage abundance 11 or 12? Fortunately, we do not actually need to know the percentage abundance for paper 1 because all we need to know is out of the 4 options we have, which one is the more likely. Because the highest abundance is for the 24 mass isotope, we can expect the relative atomic mass, RAM, to be of a value close to 24, but not exactly 24. Therefore, the only feasible option would be B. If we were looking at the relative atomic mass to be 24.9, we would expect the mass 25 isotope to be of the highest abundance, with 24 and 26 mass isotopes to be of roughly equal abundances. Successive ionization energy question. We are asked to identify which of the rows would correspond to group 13 element. Successive ionization energy question is all about identifying how there is a generally increasing trend in the successive ionization energy with a big jump. With a big jump when we have removed all the valence electrons and we start to remove an electron from the electron shell underneath. One electron shell below, smaller than the valence electron shell. Which means that for group 13s, we would expect there to be a big jump between the 3rd electron being removed, which is the final valence electron remaining, and the 4th electron, which would be from the electron shell underneath. It appears that option B has a big jump between the 3rd and the 4th, which is why we know B would correspond to a group 13 element. Trend down the group 1 and 17 usually are the opposite. To find a property, a physical property that decreases down for both group 1 and 17, we're going to have to compare and contrast each of the options. Let's start with the melting point. How does melting point change down the group for 1? Well, the metallic bond strength decreases down the group because the atomic radius increases down the group. So we know, although metallic melting point decreases for group 1, the melting point would actually increase for group 17 because the bonding nature of group 17 elements is intermolecular forces, London dispersion forces, which is dependent on the molecular size. So melting point would not be our answer. Similarly, boiling point would decrease like melting point, but increase. So again, not our answer. Electronegativity actually behaves equally. The trend for electronegativity behaves equally for both group 1 and 17, but unfortunately, electronegativity will decrease for both 1 and 17. Which means ionization energy will be our answer. And let's have a look at how ionization energy decrease down group 1 as well as 17. Well, the atomic radius is increasing, which means that the distance between the valence electron being removed and the central nucleus that is pulling the valence electron will get weaker and weaker. So easier to remove. We don't usually talk about ionization energy for non-metals, but instead electron affinity, because in reality, they will not be losing electrons, but gaining electrons to become anions. But it is possible to ionize non-metals. It's just that it will require a lot of energy. For example, we could ionize Cl gas into Cl plus an electron. Okay, but it's what I was saying about electron affinity is that it's more probable and realistic for Cl gas to obtain an electron to become Cl minus. Nevertheless, it would be more difficult to remove an electron from a positive halogen than a neutral halogen, which means the ionization energy would also decrease down the group. Oxides of period 3, phosphorus, silicon, aluminum, and magnesium. These are successive 4 elements of period 3, right? From group 15 to 2. Magnesium, aluminum, silicon, phosphorus. To the left of magnesium, we would have sodium. To the right of phosphorus, we would have sulfur and chlorine. The 4 period 3 elements we look at will have acid-base character. The acid-base character has this trend across period 3, doesn't it? Starting from the left to the right, we are basic, and then we become increasingly acid. So that phosphorus oxide, P4O10, will be acidic, while magnesium oxide will be basic. Silicon dioxide, we don't assign any acidic or basic property for one reason. It's not possible to dissolve silicon dioxide, which is a giant macromolecule. Aluminum oxide is amphoteric in that aluminum oxide can be both acidic and basic when dissolved in water. Which means our answer will be P4O10. You do need to know how to represent how P4O10 reacts with water to dissolve in, how P4O10 reacts with water to become acids, which can be indicated as P4O10 plus H2O turning into the acid form of P4O10. What is that? It's phosphoric acid, H3PO4. All we now have to do is balance numbers. So P4O10 means we would naturally produce 4 phosphoric acids. On the product side, we have 12 hydrogens, which means we would need to start with 6 water. Hopefully, the number of oxygens on the reactant side will equal to the product side, and it does. 16 on either side. Let's quickly have a look at how magnesium oxide forms basic compound in water. Magnesium oxide plus H2O will need to produce magnesium hydroxide, but magnesium hydroxide would be in the ratio of 1 magnesium for 2 hydroxides. And to balance this equation, we need not to change as it is. 1 MgO plus 1 H2O will give 1 Mg OH2. Zinc is a d block element, but not a transition metal. It's the only element in the d orbital, the first row of the orbital, d block, that's not a transition metal because of its complete d orbital. We want the transition metals to have incomplete d orbital, but zinc does not. Ligands coordinate to central transition metal ions by donating their lone pair, which by definition is also acting as Lewis base. Manganese chloride on ionic compound, where the metal is a transition metal, is paramagnetic. Paramagnetic is one of the 4 properties of transition metals. First one being variable oxidation states. Second, colored complex ion. Third being catalytic, with the 4th being paramagnetic. So all of the options are correct. Carbon to oxygen bond length can vary from a single with the bond order of 1 to a triple bond order of 3. Double bond will have the bond order of 2, but there can also be bond order of 1.5. Depends on what molecule we deal with. We are given the structural formulas, condensed structural formulas, but if we draw them out, if we display them fully, we can create a displayed formula as is drawn right here, which means for option A, we are seeing a single carbon to oxygen covalent bond. This will be the longest. Let us look at the second option, which seems to be pretty much identical, except that instead of O minus, we have OH. Option B is the ethanol, and option A is the deprotonated ethanol, which we call ethoxide. The third option seems to be different. The third option seems to be the ethanoate ion, which is the deprotonated form of ethanoic acid, which is the option D. Now, ethanoate ion has resonance. We can draw the resonance structure as follows. What is resonance structure? Alternate position of double bond. And this is represented by the movement of electrons that will delocalize across a pi system. Which means the bond order would be 1.5. One of the possible bond lengths I've mentioned at the beginning. This would be shorter than the first two, the 2 single covalent bonds. But 1.5 bond order, the 1.5 bond order covalent bond will not be as short as a double bond, which is present in ethanoic acid. Therefore, the ethanoic acid, which contains a double bond, in theory has the shortest carbon to oxygen bond length. Molecular polarity arises from how there's a net dipole moment in the molecule. For there to be net dipole moment, there needs to be the bond polarity. We need bond polarities, but we need to make sure that the bond polarities are asymmetrically distributed. For example, we would expect how the electronegativity difference between carbon and fluorine results in bond polarity, where we would have the dipole moment corresponding to this polarity represented as delta positive to delta negative. But then we've got tetrahedral molecular geometry, which cancels out the 4 dipole moments so that the net dipole moment is 0. CF4, CCl4 are of these examples. We have CH3, CHF3, and CClF3 remaining. Which one is going to be more polar? Well, let's draw them first. Let's draw them out first. So, C, I'm going to draw 3D structure so that we have a wedge and a dash. Where's the net dipole? The net dipole, we can identify how, there will be 3 dipole moments that's represented by the 3 orange lines from delta positive to delta negative. CH bond, there is not significant electronegativity difference between carbon and hydrogen such that there is no dipole moment, which means the net dipole moment for our molecule under question will be from hydrogen side to the opposite fluorine side. Let's draw CCl F3. I'm going to use a different color for this. I'm going to use blue and represent CCl F. Similarly, there will be 3 dipoles, but in fact, there's another dipole that was not present in the previous molecule. What is that? We have the additional CCl dipole moment because chlorine is more electronegative than carbon. The introduction of an additional dipole, although this dipole moment is weaker than the 3 dipole moments from CF bonds, so in order to illustrate how the CCl dipole moment is weaker than CF dipole moment, I'm going to draw the arrow to be smaller. The effect of this weaker dipole moment is that the overall net dipole moment will be weaker because the net dipole moment that is from this paper going downwards is counteracted by the upwards dipole moment of CCl, meaning that our answer would be A, not C. VSEPR theory. BRF4 minus would have how many electron domains? And out of this number of electron domains, how many bonding, how many lone pairs? Let's draw the Lewis structure first. Br will have 4 bonding pairs with 4 fluorines, which means that we will have used up 4 valence electrons of the 8 valence electrons available on Br minus. Note, we're dealing with Br minus, not Br. Therefore, 8 valence electrons instead of the normal 7. Let us put the 2 lone pairs as such, which tells us out of the 6 electron domains, which would have octahedral or square bipyramidal geometry, there are the 4 bonding and 2 lone pairs, which would correspond to square planar molecular geometry. How does metallic bond strength change between groups? Down the group, up the group, and how does group 1 metallic bond compared with group 2. Metallic bond is affected by two factors. First being the ionic charge of the metal ions in the lattice, as well as the ionic radius. So if we have high ionic charge like +3 and low ionic radius, which would be in group 2, we would have stronger metals basically with higher melting points. And we are given a list of metals with magnesium from group 2, with the rest being group 1. I started with option D, which seems to be the answer because we have magnesium, group 2, the biggest ionic charge, followed by group 1 sodium. Magnesium is right after sodium, which means magnesium will be smaller than sodium. So we want the list to start off with magnesium, followed by sodium, and then followed by potassium because potassium is bigger than sodium. Potassium is below sodium, and rubidium in turn below potassium, which puts the option D list the correct list. Let's compare the bond strength of ozone and oxygen. Ozone is represented as a combination of resonance structures. If we fully indicate the movement of delocalized electrons, we want to introduce these curly arrows. And this results in the oxygen to oxygen bond order to be 1.5, halfway between a single oxygen to oxygen and a double oxygen to oxygen bond length. This would contrast with the plain oxygen to oxygen double bond, meaning oxygen to oxygen double bond will be stronger, meaning that the wavelength of light that's used to dissociate, in other words, break oxygen bond, will be shorter, frequency higher. So out of the four statements, it appears that A is correct. Ozone bond dissociation will require less energy, as indicated by longer wavelength. Enthalpy of formation means what? Enthalpy change when 1 mole of a substance is produced from its constituent elements in its standard state. Let's make it more detailed. Enthalpy change when 1 mole of a compound in its standard state is produced from its constituent elements in their standard states. For ethanol, we want the standard state to be liquid, not gas. Carbon, hydrogen, and oxygen in their standard states would be carbon solid, hydrogen gas, oxygen gas. And we want to make sure that only 1 mole of ethanol is produced, not 2. Meaning, option C is our answer. Bond strength is indicated by the values of bond enthalpies. We can work out the enthalpy change using bond enthalpies of the reactants and products. But we're already given the enthalpy change value, which is of negative value, meaning that this reaction is exothermic, as we would expect for combustion of methane. And if we think about the significance of the negative value, the bonds newly formed will release energy. And this amount of energy released from new bonds formed will be greater than the energy inputted required for the initial bonds breakage, the existing bonds of the reactants breaking. Which means that the bond enthalpies of the products will be greater than the bond enthalpies of reactants. Let's look at the activation energy. We're going to compare the activation energy of the forward exothermic versus endothermic. Easiest way to compare would be to draw the energy profile diagram. Exothermic, we're going to have the reactants to have the higher enthalpy than the products. We will hit a transition state. Let's call this TS. There will be a curve to show the change in enthalpy, energy state. Let's label the axis as enthalpy or energy. The x-axis, reaction progress. Let's label the activation energy of the forward reaction as the red line, but the reverse endothermic reaction as the orange line, which clearly is greater than the activation energy of the forward reaction. So forward will be less than the reverse. Hydration enthalpy. Okay. We are given some lattice enthalpy values, solution enthalpy values and hydration values of one of the ions involved. We need to draw the relationship between three species, three groups of species. First one being the initial NaCl solid. NaCl solid will have a specific enthalpy, which requires a lot of energy to break into the gaseous ions Na plus and Cl minus gaseous. The energy required to convert NaCl solid into gaseous Na plus and Cl minus is what we call the lattice enthalpy. And we're given this value to be plus 790 kilojoules per mole. We also have the final group of species, which we'll call the aqueous sodium ion and Cl minus. These are hydrated Na plus and Cl minuses. Let's think about how gaseous sodium ions and chloride ions can be hydrated. All we need to do is surround the Na plus and Cl minus with water molecules. There will be a natural ionic dipole bond formed. Na plus will be, I'm going to draw this in a different color. Na plus will be forming ionic dipole bond with the delta negative part of our water, while our chlorine will be forming ionic dipole bond with the delta positive hydrogens of surrounding water molecules. The nature of this bond is electrostatic, which means that there will be energy released. Energy released will correspond to negative enthalpy value, which will be represented as minus 359. Actually, minus 359, that corresponds to Cl minus, and minus x, where x would correspond to what we're looking for, the answer we're looking for, the hydration enthalpy of Na+. The hydration enthalpy of sodium plus with Cl minus would correspond to the hydrogen enthalpy that is drawn from gaseous sodium chloride to aqueous sodium chloride. Now, the final solution enthalpy is represented by NaCl dissolving in water, which would also give Na plus aqueous and Cl minus aqueous. Let's give this value positive value as represented by the question, which means we actually need to input energy to dissolve NaCl in water. Now, all we have to do is find what x is by setting up a Hess cycle equation. Plus 790 will equal to plus 4 and minus 359. I should have actually written plus x. 4 minus 359 and minus x. Let's put x to the opposite side, meaning x equals 4 plus 359 minus 790. That was a long question, but in the end we have our option B as our answer. Which reaction becomes more spontaneous as temperature increases? Well, we need to use the equation delta G corresponding to spontaneity, and we want the value to be more and more negative, which equals to delta H minus T delta S. This is the delta, one of the three delta G equations that utilizes temperature and entropy change. In order for delta G to be negative, we would need minus T delta S to be as negative as possible, which means delta S needs to be as positive as possible. Which means the equation needs to get more and more chaotic. By chaotic, we mean higher moles of products than the reactants. Which of the four options contains higher moles of products than reactants? It appears that A has an increase in the moles of products. So A will be the answer. And like B, which actually has reduction of product moles, will not be the answer. Reaction rate monitoring. Let's see what features of this equation, of this reaction equation, we can utilize. I do see protons, so we could probably target acidity. The products will be more and more acidic than the reactants. We also have color difference between iodine, aqueous iodine, purple, and aqueous iodide, colorless. So pH meter will be a suitable method, monitoring method, because products will be more acidic. So yes, pH meter would work. Gas syringe will not work because there is no gas produced. Colorimetry would work because of the purple to color, colorless, decolorization of the reaction. 1 and 3 only. Factors that increase the rate of reaction: temperature, catalyst, concentration, surface area. We do see how increasing particle size would in fact decrease the rate, Therefore, immediately we can tell A does not increase the reaction rate. Increasing temperature will, yes, increase the rate. Let's just brainstorm how these factors lead to change in rate. Increasing temperature, increasing kinetic energy, more collision, more successful collision. But also, we have more of the molecules with energy sufficient to result in successful collision. And we indicate this by more of the molecules, reactor molecules, having energy greater than the activation energy, so that the chances of successful collision rises. Increasing concentration of the reactant sulfuric acid will increase the collision frequency. Stirring the reaction mixture is a bit like increasing the concentration because we are increasing the collision frequency. By increasing the exposure of the two reactant molecules to each other. Unit for rate constant for a third order reaction. Rate will always have the unit mole dm minus cube s to minus 1 per second. The third order concentration would be mole cubed dm to power of minus 9, which means that our K rate constant will be of unit mole minus 2 dm to the power of 6 and s minus 1. Option C. Again, the relationship between rate constant and temperature, K versus T. What's the relationship what's the equation that illustrates the relationship between K and T? Rate constant equals Arrhenius constant times exponential to the power of minus EA over RT, which indicates us that as temperature rises, the rate constant will rise exponentially. Option C. Temperature increase will be counteracted by decrease in temperature made possible by favoring the endothermic forward reaction, which means that POE, the position of equilibrium, will shift to the product side with the Kc value increasing because temperature does affect the Kc value. But note that other factors like catalyst does not affect Kc value. Spontaneity, delta G. We need to use an equation that connects delta G with Kc value, and that is delta G equals minus N, not minus N, minus R, gas constant, T, temperature, ln Kc. We want the delta G to be of negative value, which means ln K needs to be what? Needs to be positive. And for ln Kc value to be positive, we want the Kc value to be greater than 1. In other words, more products than reactants. A would be our answer. Acid deposition is different to acid rain in that acid rain is a natural phenomenon due to carbon dioxide in the air dissolving in the water vapors of rain and becoming carbonic acid. CO2 plus H2O will become H2CO3 carbonic acid. However, the human activity caused production of SO2 and NO2 will result in sulfuric acid and nitric acid, which is not natural. Therefore, we do not want to include CO2 in oxides contributing to acid deposition. Just to talk a little bit about how SO2 becomes sulfuric acid, NO2, nitric acid. Start with nitric acid. It's a bit easier. Simply speaking, add H2O, we will produce HNO3. But to make sure we have the correctly balanced equation, let's add 2 NO2, 1 H2O to give 2 HNO3. Oh, this does not balance. So let's try and balance this. How about if we produce a nitric acid and a nitrous acid? That works out. 4 hydrogens, no, 2 hydrogens, 5 oxygens, and 2 nitrogens. Perfect. As for sulfuric acid production, we will have SO2 plus oxygen that turns into SO3. Balance the number of sulfurs and oxygens. Then it is the sulfur trioxide formed that will dissolve in water to give H2SO4. Strong acid will give weak conjugate base, while weak acid will give strong conjugate base, with the logic that CH3COOH will dissociate into the conjugate base ethanoate ion, which is now the conjugate base. The definition of weak acid is that acid only partially dissociates, meaning there will be higher concentration of the original acid than the conjugate base. And the reason behind that is conjugate base, once formed via dissociation, will re-pick up a proton to revert back to the original acid form. And that is because the conjugate base is quite strong, that it readily re-picks up on H plus and goes back. This would be different to HCl, a strong acid that fully dissociates. And one of the reasons why HCl fully dissociates is because Cl- is a weak conjugate base that cannot re-pick up on H plus to go back to the original acid state. So notice how we use the equilibrium sign for weak acid dissociation, and we use a unidirectional single arrow for HCl, strong acid dissociation. But in fact, a more accurate way of saying this would be a large arrow to the product side and a small arrow to the reactant side. HCl is the only strong acid out of the 4 options, and therefore the answer. Which species is a Lewis acid but not a Bronsted-Lowry acid? In other words, which species accepts lone pairs or a lone pair but does not give off a hydrogen ion? Copper 2+ is a transition metal ion that is often coordinated by many ligands. So copper 2+ is a perfect Lewis acid that does not act as a Bronsted-Lowry acid. Ammonium ion would be a Bronsted-Lowry acid, but not a Lewis acid. And ammonium ion is in fact the conjugate acid of ammonia, which is a weak base. The conjugate acid of a weak base ammonia. The weak base ammonia, however, is the Bronsted-Lowry base as well as the Lewis base, because the mechanism of the acid-base reaction is the lone pair of nitrogen hitting on the hydrogen of the water, which is essentially donating a lone pair. Copper is a metal. It doesn't participate as a base or an acid. So copper is not going to be an option. Ethanoic acid will have a strong conjugate base. pH calculation, given that we have hydroxide ion concentration. Two ways to go on about pH calculation. First, my preferred method is, simply speaking, work out pOH. 4. Minus log 1 times 10 to minus 4, put it into the calculator, or for those of you who are good at math, can immediately tell pOH is 4. Then we know how pH plus pOH will equal to 14 from the ionic product of water, meaning the pH will be 10. Second method would utilize not the pH plus pOH equals 14, but the raw ionic product of water, H plus times OH minus, equals 10 to minus 14, where H plus concentration would equal to 10 to minus 14 divided by 10 to minus 4, which is 10 to minus 10, and therefore pH 10. Oxidation state of oxygen is usually minus 2, but there are a few exceptions. When oxygen is bonded to an atom that is more electronegative than itself, that's only fluorine, oxidation state will no longer be a negative, but a positive value. And an example of this would be OF2, in which case we would assume that each fluorine requires 1 electron, meaning 2 fluorines will contribute to the minus 2 charge, meaning oxygen will have to be plus 2 charge. Oxygen bonded to itself, there's no electronegativity difference, and the oxidation state will be 0. Hydrogen peroxide. Is another exception, where oxygen is bonded to itself as well as to a hydrogen. Do the math. H plus H2 will have plus 1 charge, meaning overall 2 H's will contribute 2 plus charge. That needs to be balanced by 2 oxygens contributing minus 1 each. Voltaic cell question. We're dealing with iron versus silver, where we're given that iron is going to be oxidized and silver reduced. Iron is the reducing agent. Let's note how iron will occupy the anode, where oxidation takes place. Silver, cathode, where reduction takes place. What we're asked is, does Fe iron occupy anode or cathode? We know it will be anode. And silver, direction of electron flow will always be from anode to cathode, because where there's the oxidation, there will be the electrons released that can travel to the cathode to be used to reduce metal cations. So from our voltaic cell diagram, right to left, because anode is on the right. Conditions that affect, factors that affect moles of electrons flowing would be the current, duration, and the ionic charge, where there will be positive correlation between the moles of electrons flowing with current and duration, but inverse correlation with the ionic charge, because if this is a higher ionic charge, that means we need more electrons to that needs to be used for reduction. Therefore, to deposit the greatest mass of copper, we want the highest current possible, which would be, in our case, 5A. Then we would want the least ionic charge, the smallest ionic charge, so that we can produce most amount of the greatest mass of copper. When it comes to electroplating, all we need to remember is that in the anode that is positive, there will be oxidation of the metal electrode. So whatever we want to electroplate with, so if we want to electroplate with silver, we need to make sure that the anode is silver, that will oxidize into Ag+, that will travel towards the cathode. Now this will be the object we electroplate. In this case, zinc. Not very well written, but that reads as Zn, zinc. Once silver plus ion, Ag+ ion, arrives at the cathode, it will be reduced to silver metal solid that becomes deposited as a layer of silver on the object zinc cathode. Anode would be our silver, cathode our zinc. C, anode is made of silver. Organic molecule naming, IUPAC nomenclature. Let's remember, the first starting point is working out the functional group that will occupy the suffix. Remember, IUPAC nomenclature is composed of prefix, suffix, with stem in between. We're dealing with an alkene. And this alkene is branched. So we need to think about the branched that will occupy the prefix. But for now, let us assign the stem by working out the longest carbon chain, which seems to be a 6-carbon chain, starting with carbon 1, 2, 3, 4, 5, and 6, which means we're dealing with a hexene, but more specifically, hex 2-ene, because the double bond is between the second carbon and the third carbon. We have the stem, the suffix, and all we need to do is recognize the presence of these 3 methyl branches, which we will describe as trimethyl. 3 methyls, trimethyl. Now let's indicate the positions of these 3 trimethyls, of these 3 methyls, as 2-, 3-, 5-, no, 2, 3, 5-. 2, 3, 5- trimethyl hex 2-ene. Do we have this name? Yes, we do, as option D. Decolorization of bromine. Water in the dark is about electrophilic addition of bromine into a double bond or triple bond, which means we want the reactant to be hex 1-ene, an alkene. The rest are all alkanes or cycloalkanes, which would require sunlight to react with bromine via free radical free radical substitution reaction. Oxidation of alcohol to produce carboxylic acid, we'll be using oxidizing agent potassium dichromate, K2Cr2O7, or KMnO4, potassium manganate. What we need to recognize is that there's a difference between how primary alcohols can be oxidized to aldehyde first, and then further oxidized to carboxylic acid, while secondary alcohols can only be oxidized to ketones. We're given 3 alcohols, out of which we have to find the primary alcohol, that is prop-1-O. Prop-2-O, because it's a secondary alcohol, will only give propanone and not propanoic acid. Let's look at the third option, 2-methyl-prop-2-O. Let's look at the displayed structural formula. Well, this is what we call a tertiary alcohol that does not have any room for oxidation. For oxidation, there needs to be hydrogen lost. And where's the hydrogen lost from? It's lost from the central carbon to which the hydroxyl group, alcohol group, is bonded to. This tertiary 2-methyl-prop-2-O does not have any hydrogen, a tertiary alcohol that will not oxidize at all. Nitration of benzene will be using NO2 plus as our electrophile, nitro group, where there will be the electrophilic substitution. Remember how this is substitution, meaning there will have to be one of the hydrogens bonded to the carbon to which NO2 will bind. The carbon to which NO2 will bind to will originally have a hydrogen bonded, which will be removed. So that we end up with a nitrobenzene and an H+. HNO3 is indeed required for nitration of benzene. It is used for production of the nitro group in the first place by reacting with sulfuric acid, which will produce our desired product, nitro group, from how H2SO4 would contribute an H plus to the OH minus produced from HNO3. So yes, nitric acid is used, but not as the electrophile, but as the production, as a reagent needed for the production of our electrophile nitro group. But-1-ene and HBr is electrophilic addition. Electrophilic addition to convert an alkene to a halogenal alkane, but a complex one, because we are using asymmetrical alkene and hydrogen halide, for which we will have to apply the Markov rule. But-1-ene, if we draw, will be an asymmetrical alkene as follows. To which there will be the addition of our electrophile, where the delta positive, the polar positive hydrogen, will be facing the double bond for electrophilic attack, while the polar negative bromine atom will be facing away, giving a carbocation intermediate. The carbocation intermediate will have a positive charge, to which bromide ion will bind to. And this will produce, in our case, 2-bromobutane, which is the major product formed. Which means there will be a minor product formed from a different carbocation intermediate that arises. Instead of the positive charge being on second carbon, we could have the positive charge on the first carbon, carbon 1, to which the bromide ion will attack and form 1-bromobutane. Major product is going to be the 2-bromo, while 1-bromo will be the minor product. What's the reason? Well, carbocation intermediate is not really stable because of the positive charge on the carbon. For the successful attack of bromide ion on the carbocation intermediate to accomplish the product halogen alkane, we need the carbocation intermediate to survive until the attack. To maximize the survival of the carbocation intermediate, we need to stabilize the central carbon, positive carbon, as much as possible, which is possible via the positive inductive effect of the surrounding alkyl groups, for which the major carbocation intermediate has 2 alkyl groups on the left and right, reducing the positive charge on the central carbon. This will contrast with only one alkyl group contributing the positive inductive effect, and therefore not as well stabilizing the positive carbon atom. Enantiomer, stereoisomer, is all about finding chiral molecules, and we need to make sure that we are able to identify a chiral center, a central carbon atom that has 4 different distinct groups bonded to it. Looking at option A, we could potentially think the third carbon is a chiral center because it has a hydrogen, hydroxyl, and alkyls. Unfortunately, the alkyls are identical ethyl alkyl groups, meaning there are only 3 distinct groups. Does not qualify as an enantiomer. The second and the third contains double bonds, which means it's likely to be geometric isomers. So let's ignore these for now. And we can ignore these unless the final option is not the answer. But fortunately, the final answer is the right one, because immediately looking at the option D molecule, we can identify how the second carbon has a bromine group bonded to it. So potentially a chiral center, and let's count if there are 4 distinct groups. First, bromine, hydrogen, a methyl, and a propyl. Drawing this 3D, we can draw carbon at the center with bromine, hydrogen, methyl, and a propyl. 4 different distinct groups that allows us to create a non-superimposable mirror image. If we draw, we can draw the mirror image as follow. C CH3 HBr. These 2 mirror images are enantiomers, what we call enantiomers, because they have the same structural formula, but they have different spatial arrangements of the 4 different groups around the carbon. They are not superimposable. Absolute versus percentage uncertainty. We're given the raw data of mass in grams and its absolute uncertainty. We are asked to calculate the percentage uncertainty for the calculated value, which means we do need to convert the absolute uncertainties into percentage uncertainty first, and then add the percentage uncertainties that are involved in the multiplication together to find the total percentage uncertainty of our Q value. How do we convert the absolute to percentage uncertainty? Well, what we will do for mass is 0.2 grams over 20 grams times 100, which will give us 1% for the mass. Likewise, 1 degree Celsius over 10 degrees Celsius times 100, which will give us 10%. What we need to do is multiply the two percentage uncertainties together, add these two percentage uncertainties together to get the value 11%. Index of hydrogen deficiency, IHD. What's the concept? The concept is that how many pairs of hydrogen do we save up, do we remove from a straight chained hydrocarbon if we have a double bond, a triple bond, or a cyclic form. So we have cyclohexanol, which means C6H11OH is the molecular formula for cyclohexanol. And if it wasn't cyclic, in other words, hexanol C6H13OH, how many pair of hydrogens have we saved up? That's the question. We are usually taught to do this calculation where X refers to the number of carbons and H, Y. It's difficult to remember. It takes time. I don't like that method. Just look at the presence of a double or triple and cyclic form. Going from straight chained hexanol to cyclohexanol, we've saved up 1 pair of hydrogen, which means IHD will be 1. NMR. Let's interpret this chemical shift data. The easiest way to go about is not interpret from scratch, but look at individual options and see if we have a match. So, looking at the first option, we have potentially a hydroxyl group that will be distinct as well as a double bond. Our job is to see if one of these two will correspond to the peak near chemical shift 10 ppm. So let us go to data booklet and see if double bond or a hydroxyl group would have a similar value. At the bottom of the table, we have OH group 1 to 6 and a double bond, carbon to carbon double bond, neither of which will match the 10 ppm value. So we will cross the first option out. Second option, butanol, we'll try and look for the chemical shift of the characteristic carbonyl group for aldehyde, not ketone. So let us see if we can find the aldehyde group, which is not going to be on the first page, but on the second page. Yes, we have found our near 10 ppm functional group. that contains the hydrogen, aldehyde group. So the data we have is an aldehyde. Therefore, we have located our answer in option B. That's the end of paper 1 for today from November 20. Hope that was helpful and useful. Good luck to you all.